Graph theory and network flows. In the modern world, planning efficient routes is essential for business and industry. With applications as varied as product distribution, laying new fiber optic lines for broadband internet, and suggesting new friends within social network websites like Facebook. This field of mathematics started nearly 300 years ago as a look into a mathematical puzzle. We'll look at it in a bit. The field has exploded in importance in the last century, both because of the growing complexity of business in a global economy and because of the computational power that computers have provided us. Graphs. Drawing graphs. Example 1. Here's a portion of a housing development from Missoula, Montana. As part of her job, the development's lawn inspector has to walk down every street in the development, making sure homeowners' landscaping conforms to the community requirements. Naturally, she wants to minimize the amount of walking she has to do. Is it possible for her to walk down every street in this development without having to do any backtracking? While you might be able to answer that question by looking at the picture for a while, it would be ideal to be able to answer the question for a picture regardless of its complexity. To do that, we first need to simplify the picture into a form that is easier to work with. We can do that by drawing a simple line for each street. Where streets intersect, we will place a dot. This type of simplified picture is called a graph. Graphs, vertices, and edges. A graph consists of a set of dots called vertices and a set of edges connecting pairs of vertices. While we drew our original graph to correspond with the picture we had, there is nothing particularly important about the layout when we analyze a graph. Both of the graphs below are equivalent to the one drawn above since they show the same edge connections between the same vertices as the original graph. You probably already noticed that we are using the term graph differently than you may have used the term in the past to describe the graph of a mathematical function. Example 2. Back in the 18th century, in the Prussian city of Königsberg, a river ran through the city and 7 bridges crossed the forks of the river. The river and the bridges are highlighted in the picture to the right. As a weekend amusement, townsfolk would see if they could find a route that would take them across every bridge once and return them to where they started. Leonhard Euler, one of the most prolific mathematicians ever, looked at this problem in 1735, laying the foundation for graph theory as a field of mathematics. To analyze this problem, Euler introduced edges representing the bridges. Since the size of each landmass, it is not relevant to the question of bridge crossings. Each can be shrunk down to a vertex representing the location. Notice that in this graph, there are 2 edges connecting the north bank and island, corresponding to the 2 bridges in the original drawing. Depending upon the interpretation of edges and vertices appropriate to a scenario, it is entirely possible and reasonable to have more than one edge connecting 2 vertices. While we haven't answered the actual question yet of whether or not there is a route which crosses every bridge once and returns to the starting location, the graph provides the foundation for exploring this question. Definitions. While we loosely defined some terminology earlier, we will now try to be more specific. A vertex. A vertex is a dot on the graph that could represent an intersection of streets, a land mass, or a general location like work or school. Vertices are often connected by edges. Note that vertices only occur when a dot is explicitly placed, not whenever 2 edges cross. Imagine a freeway overpass. The freeway and side street cross, but it is not possible to change from the side street to the freeway at that point. So there is no intersection and no vertex would be placed. Edges. Edges connect pairs of vertices. An edge can represent a physical connection between locations, like a street, or simply that a route connecting the 2 locations exists, like an airline flight. Loop. A loop is a special type of edge that connects a vertex itself. Loops are not used much in street network graphs. Degree of a vertex. The degree of a vertex is the number of edges meeting at that vertex. It is possible for a vertex to have a degree of 0 or larger. Path. A path is a sequence of vertices using the edges. Usually, we are interested in a path between two vertices. For example, a path from vertex A to vertex M is shown below. It is one of many possible paths in this graph. Circuit. A circuit is a path that begins and ends at the same vertex. A circuit starting and ending at a vertex A is shown below. Connected. A graph is connected if there is a path from any vertex to any other vertex. A graph drawn so far has been connected. The graph below is disconnected. There is no way to get from the vertices on the left to the vertices on the right. Weights. Depending upon the problem being solved, sometimes weights are assigned to the edges. The weights could represent the distance between two locations, the travel time or the travel cost. It is important to note that the distance between vertices in a graph does not necessarily correspond to the weight of an edge. Shortest path. When you visit a website like Google Maps or use your smartphone to ask for directions from home to your aunt's house in Pasadena, you're usually looking for a shortest path between the two locations. These computer applications use representations of the street maps as graphs with estimated driving times as edge weights. While often it is possible to find a shortest path on a small graph by guess and check, our goal in this chapter is to develop methods to solve complex problems in a systematic way by following algorithms. An algorithm is a step-by-step procedure for solving a problem. Dijkstra's algorithm will find the shortest path between two vertices. Dijkstra's algorithm. 1. Mark the ending vertex with a distance of 0. Designate this vertex as current. 2. Find all vertices leading to the current vertex. Calculate their distances to the end. Since we already know the distance the current vertex is from the end, this will just require adding the most recent edge. Don't record this distance if it is longer than a previously recorded distance. 3. Mark the current vertex as visited. We will never look at this vertex again. 4. Mark the vertex with the smallest distance as current and repeat from step 2. Example 3. Suppose you need to travel from Tacoma, Washington, vertex T, to Yakima, Washington, vertex Y. Looking at a map, it looks like driving through Auburn, A, then Mount Rainier, MR, might be the shortest. But it's not totally clear since the road is probably slower than taking the major highway through North Bend in B. A graph with travel times in minutes is shown below. An alternate route through Eatonville, E, and Packwood, P, is also shown. Dijkstra's algorithm is an optional algorithm, meaning that it always produces the actual shortest path, not just the path that is pretty short, provided one exists. This algorithm is also efficient, meaning that it can be implemented in a reasonable amount of time. Dijkstra's algorithm takes around v-squared calculations, where v is the number of vertices in a graph. A graph with 100 vertices would take around 10,000 calculations. While that would be a lot to do by hand, it is not a lot for a computer to handle. It is because of this efficiency that your car's GPS unit can compute driving directions in only a few seconds. In contrast, an inefficient algorithm might try to list all possible paths, then compute the length of each path. Trying to list all possible paths could easily take 10 to the 25th calculations to compute the shortest path with only 25 vertices. That's a 1 with 25 zeros after it. To put that in perspective, the fastest computer in the world will still spend over 1,000 years analyzing all those paths. Euler's circuits and the Chinese postman problem. In the first section, we created a graph of the Königsberg bridges and asked whether it was possible to walk across every bridge once. Because Euler first studied this question, these types of paths are named after him. The Euler path. An Euler path is a path that uses every edge in a graph with no repeats. Being a path, it does not have to return to the starting vertex. Example 5. In the graph shown below, there are 7 Euler paths. One such path is CAB DCB. The path is shown in arrows to the right and the order of the edges numbered. The Euler circuit. An Euler circuit is a circuit that uses every edge on a graph with no repeats. Being a circuit, it must start and end at the same vertex. Example 6. The graph below has 7 possible Euler circuits. Here's a couple, starting and ending at vertex A. The second is shown in arrows. Look back at the example used for Euler paths. Does that graph have an Euler circuit? A few tries will tell you no. That graph does not have an Euler circuit. When we were working with shortest paths, we were interested in the optimal path. With Euler paths and circuits, we're primarily interested in whether an Euler path or circuit exists. Why do we care if an Euler circuit exists? Think back to our housing development lawn inspector from the beginning of the chapter. The lawn inspector is interested in walking as little as possible. The ideal situation would be a circuit that covers every street with no repeats. That's an Euler circuit. Luckily, Euler solved the question of whether or not an Euler path or circuit will exist. Euler's path and circuit theorems. A graph will contain an Euler path if it contains at most 2 vertices of odd degree. A graph will contain an Euler circuit if all vertices have even degree. Example 7. In the graph below, vertices A and C have degree 4, since there are 4 edges leading into each vertex. B is degree 2, D is degree 3, and E is degree 1. This graph contains 2 vertices with odd degree D and E and 3 vertices with even degree A, B, and C. So Euler's theorems tell us that the graph has an Euler path but not an Euler circuit. Example 8. Is there an Euler circuit on the housing development lawn inspector graph we created earlier in the chapter? All the highlighted vertices have odd degree. Since there are more than 2 vertices with odd degree, there are no Euler paths or Euler circuits on this graph. Unfortunately, our lawn inspector will need to do some backtracking. Example 9. When it snows in the same housing development, the snowplow has to plow both sides of every street. For simplicity, we'll assume the plow is out early enough that it can ignore traffic laws and drive down either side of the street in either direction. This can be visualized in the graph by drawing 2 edges for each street, representing the 2 sides of the street. Notice that every vertex in this graph has even degree, so this graph does have an Euler circuit. Now, we know we have to determine if a graph has an Euler circuit, but if it does, how do we find one? While it is usually possible to find an Euler circuit just by pulling out your pencil and trying to find one, the more formal method is Fleury's algorithm. Fleury's algorithm. 1. Start at any vertex if finding an Euler circuit. If finding an Euler path, start at one of the 2 vertices with odd degree. 2. Choose any edge leaving your current vertex, provided deleting that edge will not separate the graph into 2 disconnected sets of edges. 3. Add that edge to your circuit and delete it from the graph. 4. Continue until you're done. Example 10. Let's find an Euler circuit on this graph using Fleury's algorithm, starting at vertex A. The Eulerization and the Chinese postman problem. Not every graph has an Euler path or circuit, yet our lawn inspector still needs to do her inspections. Her goal is to minimize the amount of walking she has to do. In order to do that, she will have to duplicate some edges in the graph until an Euler circuit exists. Eulerization. Eulerization is the process of adding edges to a graph to create an Euler circuit on a graph. To Eulerize a graph, edges are duplicated to connect pairs of vertices with odd degree. Connecting 2 odd degree vertices increases the degree of each, giving them both even degree. When 2 odd degree vertices are not directly connected, we can duplicate all edges in a path connecting the 2. Note that we can only duplicate edges, not create edges where there wasn't one before. Duplicating edges would mean walking or driving down a road twice. while creating an edge where there wasn't one before is akin to installing a new road. Hamiltonian circuits and the traveling salesman problem. In the last section, we considered optimizing a walking route for a postal carrier. How is this different than the requirements of a package delivery driver? While the postal carrier needed to walk down every street edge to deliver the mail, the package delivery driver instead needs to visit every one of a set of delivery locations. Instead of looking for a circuit that covers every edge once, the package deliverer is interested in a circuit that visits every vertex once. Hamiltonian circuits and paths. A Hamiltonian circuit is a circuit that visits every vertex once with no repeats. Being a circuit, it must start and end at the same vertex. A Hamiltonian path also visits every vertex once with no repeats, but does not have to start and end at the same vertex. Hamiltonian circuits are named for William Rowan Hamilton, who studied them in the 1800s. With Hamiltonian circuits, our focus will not be on existence, but on the question of optimization. Given a graph where the edges have weights, we can find the optimal Hamiltonian circuit, the one with the lowest total weight. This problem is called the traveling salesman problem, TSP, because the question can be framed like this. Suppose a salesman needs to give sales pitches in 4 cities. He looks up the airfares between each city and puts the cost in a graph. In what order should he travel to visit each city once, then return home with the lowest cost? To answer this question of how to find the lowest cost Hamiltonian circuit, we will consider some possible approaches. The first option might come to mind is just to try all different possible circuits. Brute force algorithm, aka exhaustive search. 1. List all possible Hamiltonian circuits. 2. Find the length of each circuit by adding the edge weights. 3. Select a circuit with minimal total weight. The brute force algorithm is optimal. It would always produce the Hamiltonian circuit with minimum weight. Is it efficient? To answer that question, we need to consider how many Hamiltonian circuits our graph could have. For simplicity, let's look at the worst case possibility where every vertex is connected to every other vertex. This is called a complete graph. Suppose we had a complete graph with 5 vertices like the air travel graph above. From Seattle, there are 4 cities we can visit first. From each of those, there are 3 choices. From each of those cities, there are 2 possible cities to visit next. There is then only 1 choice for the last city before returning home. Number of possible circuits. For n vertices in a complete graph, there will be n minus 1 factorial equals n minus 1 multiplied by n minus 2 multiplied by n minus 3 and so on, 3 multiplied by 2 multiplied by 1 routes. Half of these are duplicates in reverse order, so there are n minus 1 factorial divided by 2 unique circuits. The exclamation symbol is read factorial and is shorthand for the product shown.